So our next speaker is Clothilde Langlais, who's going to talk to us about modelling the reef's past and future, upwelling, warming and resilience in a changing climate. I'll give you a warning at 10 minutes.
Thank you. So I was going to start by saying we're going to go to higher scale, but actually not. We're going to go back to larger scale, but kilometer scale. So I'm going to talk about the challenge the GBR faces in a changing climate and its ability to adapt. So we're going to the tropics as well. So the GBR is recognized globally as a ecological, economic, and cultural big value, and it's recognized through the UNESCO. So to try to protect the value of the GBR, the Australian and the Queensland government developed those two plans over the years. And that's under this context of those plans that the big reef project was born. So it was born in 2010. And it was sort of born to try to monitor and model the environment to inform the adaptation and the management of the Great Barrier Reef. So initially, it was sort of developed in a water quality perspective, and that's why it was sort of there with the movie to look at what's happening in the catchment all the way to the reef and what the marine environment is doing to it. But with the reef system, you can actually track all the different threats to the GBR. So I like that slide. It's coming from the reef snapshot from last summer. So the reef snapshot is sort of the equivalent of the state of the climate for more the climate people, but focused on the GBR. It's sort of showing all the threats that happened last season. But it's showing the climate trend as well as the climate extreme. So at the bottom, you've got this long warming trend that happened from last century to now. But on top of it, you've got those extreme. And what matters in the GBR, it's the flood. So we've got flood in the last 3 years now, the last 3 summers, the tropical cyclone, and the widespread bleaching event. We actually had 6 mass coral bleaching events in the last decade. That's what's hammering the system. That's what reducing the ability to recover is just coming over and over again. There's maybe a bit of hope in that picture, which is there might be some areas that are less susceptible to the bleaching. And so here there's a map of bleaching risk. So it's through heat accumulation metrics we're doing this. It's sort of showing that the blue area are the safe area from bleaching risk. And we've got one in the north, in the far north GBR, and one in the south, in a Swan area. And when you compare that with the general circulation, it becomes evident that the upwelling system along the shelf break are sort of protecting, or are possibly protecting the system. When you go at depth as well, that's sort of the 3 line, you've got less risk as well. So the depth and the geographic area with the upwelling might be a place to protect from the warming. So this upwelling footprint has been shown to persist into the future in the 50s and the 80s. However, here, Cha was just looking at the seasonal mean footprint of those upwelling, but the upwelling are actually highly dynamic. So today I'd like to look into the drivers of those dynamic upwelling and the fact that they're very intermittent. So that's an example here from Jessica's paper showing 4 different events of upwelling in the central GBR. They're all very different. They're all very, intermittent. So to do that, I'm using the reef hindcast and also the climate downscaling into the future using the ACCESS-MIP. So we're using the reef system to go into the future. So we're very lucky in, I guess, in the GBR. Or first, we're going to look through the reef system. So it's based on the CSIRO environmental modeling suite called EMS. It's a hydro, wave, sediment, BGC, optics, and one more model. But today, I'm just going to focus on the hydrodynamics. For the hydro, so I'm using the 4K version of the model, and there's 4 main forcing. This is where we rely enormously on the ACCESS community. We just use the Brand and Barrari analysis at the boundary condition. And then for the rivers, we rely on the Queensland government Dead Sea catchment modelers. And we've got 64 rivers from them to push into that system, and the global tide. When we go to the climate downscaling, we've been using the ACCESS-MIP. So today I'm going to mainly show you some output when we used CMCC at the boundary, but there's going to be a few results from CESM and FGOLS as well. And for the river, we're using some machine learning technique, but I'm not going to talk about that today. So, observation. We're very lucky in the GBR, and we've got long-term monitoring at few key area from the IMOS mooring, especially in palm passages. So here that's Hofmüller from the observation, showing those intrusion at the bottom, this cold water mass that's coming in and out of the system. So we can compare that with the reef Eincast, and we kind of got very good correlation and good error. What I'd like you to zoom on, if we look at just 2 seasons there, so at 25 meters, so that's sort of close to the surface, what we see is really the onset of warming in a summer. And we can see that the onset was earlier in 2023, and the model captured that. Now, if you look at the bottom, that's 65 meters. That way, we've got those pulses of cold water. Some years, the pulse is actually quite persistent. That's what happened in 2020, and sometimes it's more intermittent in 2023. So there's restratification, destratification, restratification, destratification, and the model sort of captured that quite well as well. Like the advantage of the model, and then you can go 3D and have a 3D view of what's happening with those upwelling. So here there's a section going through palm passage of temperature and salinity and chlorophyll, and the red cross is where the mooring is. On the top left, this is the arrow, actually the wind, and we'll follow the bottom. So it's the bottom temperature going onto the shelf of the shelf and then staying at 150 meters deep. That's why we got this cold band showing up, which is where the upwelling at the shell break is happening. So when you use the model, you can sort of track back to the drivers. And the drivers here are going to be either the wind, so wind-driven upwelling, or the western boundary current, that's going to be a current-driven upwelling. And you can see how the current, so the gray dashed line, that's the current, and you can see how it's tilting the isopycnol and bringing the cold water onto the shelf. This is a cold water upwelling, but also quite salty upwelling, and you can see how, where the upwelling is located, we've got a higher signal in a deep chlorophyll maximum. So now let's try to go back to the driver, and what's more important? Is it the wind? Is it the shell break current? When we looked at all the events over those 15 years, what we found is that it's not necessarily the wind driving everything. So the northwesterly wind are the one that's going to be upwelling favorable, when the trade wind has downwelling favorable. But the events are all happening in a trade wind situation, but when the trade winds are quite weak, close to 0. And all those upwelling are happening when we've got a EAC, so a southward flowing western boundary current. So it's really the shell break current, the EAC, that is driving the dynamics of all those upwelling when you look at the 15 years time scale. So now let's have a look at what's happening into the future in this 1.5 and 2 degree warming world. So it's just to put a bit of context of how CMCC looks like in the middle of a larger ensemble of CMIP6. So we use 2 slices, so the 1.5 warming and the 2 degree warming world. So that's sort of the one we've done the downscaling for, just to try to assess the state of the GBR in that situation. So to look at the impact of the climate onto the upwelling setup, I like to separate that into spiciness and eve. And the spice will be like the change in the water mass characteristic. So we looked in the Coral Sea to see what was the change in the IRES-MIP model. So here there's 3 of them. So what you can see in the Coral Sea, we've got this warming signal at the surface. There's a deepening of the warming signal, but more importantly here, there's a cooling signal underneath. So we've got this cold water sitting just underneath that is potentially the water mass that's going to be upwelled at the shell break. If you look at the EAC, we actually found that there was a southward shift of the bifurcation point and a slowdown of the EAC. So weakening of the EAC, so less tilting of your isopycnol. So when you put that all together and you look at what it's doing to the upwelling system, what we get to is that at 1.5, so in the middle, we can see the cooling at depth, and that cooling signal is actually upwell at the shell break, which means that the mesophotic reef are actually in a cooler situation in a 1.5 warming world. And at the surface, we've got weaker warming as well. When you go to the 2-degree warming world, which is the one next to it, we still have this cooling at the bottom, but it's not upwelled anymore. So we've got now a warming of the mesophytic area and an acceleration of the warming. Oh, that's there. All right, so just now to go to those intermittent, that's what's happening at the Palm Passage mooring in those models. So we've got the dynamic happening. We've got those incursions at depth in our climate downscaling. If you look at the 1.5, we sort of have warming at the surface, but at the subsurface, we still have cold patch that actually the same temperature that in the reference. But if you go to a 2-degree warming world, there's a deepening of the warming signal at the surface, and on the shelf, those intrusion of cold water starts to be warmer. But there's sort of delay in that warming of those subsurface water mass, and I think that's due to this offshore cooling. So at the take-home message for this community, I wanted to go back to this cooling in the Coral Sea, and I think this cooling is coming from the change in the outcropping of isopycnol in the southern hemisphere, and then we've got a cooling signal propagating along those isopycnol layers. So my message for the kind of global climate modelers today is that this time of information is actually very important for the coastal modeler. And to the coastal modeler regional, I'd like to tell everybody that we have to look into those climate signals. We have to look and listen to the climate community to understand what is the important climate information going all the way to our coast. And then the depth of that cooling is very important. So the result I show you is from CMCC. You can see there that F-goals got a deeper cooling signal. When we downscale inside F-goals, we actually don't have, the cooling signal is not upwelled onto the coast. So the depth of that cooling is actually quite critical to know if we're going to have cooler or warmer condition in the mesophytic area. And that's it.
A couple of minutes for questions. Can't see you there, Andy.
Thanks. Yeah, this is a nice result about the cooling propagating in. I didn't quite understand why the EAC weakens under the stronger warming conditions.
So
do you have any idea what's going on there?
So that the bifurcation. So because it bifurcates further south, actually more flow going to the north. The bifurcation point is further south, but the jet is not necessarily moving, so there's more water going to the north.
Can I ask why the bifurcation point moves to the south, or would that be too much?
No, that's not. That's the wind curl.
Oh, we're going over there. Okay.
Thanks for the great talk. I was wondering if there are kind of biological implications of the change in the bifurcation as well, in terms of larval transport, and whether you might expect to see some community changes or, yeah, anything from that.
Yes, probably. And that's, so at the moment we don't have the full BGC in those climate downscaling, but that's the next step, early next year. So we actually want also to go all the way to a fully BGC hydrocopal system. But yeah, there will be implication to the connectivity matrix in the GBR. Although we also want to go to the 1K model to answer that question. The 4K is not quite right to do the connectivity matrices.
Okay, thank you. I think we'll move on there. Thanks, Clothilde.